All right, everyone. So we're gonna wrap up wrap up the first week today. Remember that the first homework is due on Monday. So if you have any questions about it, please don't hesitate to send me an email, and I will respond to you as quick as I can. So today um, we're gonna cover a nice topic. This one should be pretty enjoyable. This is kind of one of my favorite topics to discuss because it's kind of fun. So what we're going to talk about is what's called continuity. Right, so the first question that we want to ask to just kind of motivate where we're going to go is what do we mean by continuity non-mathematically? Again, we have these mathematical terms for various things we've had, like limit, and to give us an idea of what it actually means, it's useful to think about what it means non-mathematically. And then what we'll ask is, well, how does non-mathematical continuity relate to mathematical continuity? And then also, why do we care about continuity? Okay, so if we were doing this as a regular class, at this point I would go and ask for anyone to go and give me the example that I'm going to give next. Then I would always have a small prize with me. So unfortunately, I can't do that. But we can give an example of non-mathematical continuity, and the example I'm going to give is from movies. So the idea with continuity in a movie is that you have some event, and all of the events that came before it, and all of the events that came after it, everything all nicely fits together, so everything makes sense. Right? So an example that we can use is let's look at how the Infinity Gauntlet has been used in the Marvel Cinematic Universe. So the first time an Infinity Gauntlet appears in an MCU movie is a very brief shot of an Infinity Gauntlet in the first Thor movie. So it occurs about 10, 12 minutes into the movie when some of the Frost Giants are breaking into Odin's treasure room. And what we can see here is there's this Infinity Gauntlet sitting in the background. And of interest, it's a right-handed gauntlet, and we can also see that it's lit up. So there are stones on this Infinity Gauntlet. In fact, we can see 6 of them. So we have what appears to be a fully functional right-handed Infinity Gauntlet sitting in Asgard, back in the first Thor movie. But then at the end of Age of Ultron, so a film that came after the first Thor movie, we see Thanos reach into whatever vault that he has and pull out a left-handed Infinity Gauntlet that has no stones on it. So immediately this raises an issue of continuity. Two apparent there are apparently two Infinity Gauntlets sitting in the Marvel Cinematic Universe, but Odin has all of the stones already. But at the same time, we also know that in looking back on things, there were stones scattered throughout the universe. So you had the Power Stone, was with what the Guardians of the Galaxy were chasing. You had the Mind Stone was in Loki's scepter. You had the Space Stone was in the Tesseract, and you had the Ether, which was one of the main themes for Thor: The Dark World. So at the same time that you have apparently all of these stones on an Infinity Gauntlet in Odin's treasure room, they're also scattered throughout the Marvel Cinematic Universe, and that really makes no sense at all. So this would be what we would call a continuity issue. We have events coming before. We have the Infinity Gauntlet isn't fitting very well with the sequence of events. And then, as we can see, the main plot line of Infinity War was Thanos going around to collect all of these stones, but apparently they were already sitting in Odin's treasure room. But conveniently, there is an important plot point that was somewhat minor in Thor Ragnarok, and it was to just declare the original Infinity Gauntlet to be a fake. So what that did was it resolved the major continuity issue around this Infinity Gauntlet that had been sitting in Odin's treasure room since the first Thor movie. Just declared a fake and all of the stones on them to also be fakes. So now everything else makes sense. Um, if I wanted to pick on other continuity issues, I suppose I could pick on the X-Men series, but at that point that's just not fun because that entire franchise is basically a continuity error. Okay, so this gives us an idea of what mathematical or non-mathematical continuity means. It means that we have some event that fits nicely in with the events that come before it and the events that come afterwards. And that's going to kind of be what we talk about with mathematical continuity. So what we'll say is that we have a function is going to be continuous at a point if the limit as x goes to a of f of x equals f of a. And there are three things that we need to check. So first we need to check that the function is defined. The second one is that the limit also needs to exist, and the third is that the limit as x goes to a of f of x is a. Okay, now one of the things that we've said, and we said this not yesterday but the day before, was that whenever you have a polynomial, so if f of x is a polynomial, the limit as x goes to a of f of x is f of a for every polynomial. So what this says is that polynomials are continuous and they're also nicely continuous everywhere. And that's a fact we're going to take advantage of. Okay, so we have one example here. So we have an f of x that is defined piecewise. So it is defined as x for any x value less than -1, and x squared for any x value that's at least -1. So what we want to see is f of x continuous at the point -1? And to do it, we just need to go through these 3 points in this checklist. So if our function is going to be continuous, all 3 of these properties need to be there. If even one of them fails to be true, then we have a point of discontinuity. We are going to ask, is f of -1 defined? Well, clearly it is, because from the definition, if x is -1, we come right here and we say f of x will be x squared, so f of -1 is going to be -1 squared, which is 1. Okay, so then we come to point 2. Does the limit as x goes to -1 of f of x exist? Well, here we have is the definition of the function is changing between the left and the right side of at -1, so we're going to want to use a left limit and a right limit and compare those two. So first we'll take the left limit at -1, so the left limit at -1 for f of x is just going to be the limit as x goes to -1 from the left of x. Because again, for the left limit, we're only looking at x values that are less than -1. From our definition of f, we're going to use the top part of the definition. And because we're looking at a polynomial there, and we said that polynomials are continuous everywhere, we can just plug in the value x equals -1 and get that our limit as x goes to -1 from the left of f of x is -1. Okay, well then we need to look at the right limit. So for the right limit, we're going to be looking at x values that are bigger than -1. So our right limit at -1 of f of x, we're going to use the second half of the definition for f. So we'll get the limit as x goes to -1 from the right of x squared. Again, we have a polynomial, so we can plug in x equals -1. And here we're going to get a limit of 1. So the left limit at -1 is -1. The right limit at -1 is 1. So the left and the right limits don't agree, which tells us that the limit as x goes to -1 of f of x does not exist, and therefore one of our 3 points in that continuity checklist failed, which tells us that our function is discontinuous at -1. Okay, so in the same way that we had rules for limits, so when we had a limit of a sum or a difference or limit of a function times a constant, and then we had also products, quotients, and power rules in there, we have the same kind of things showing up for continuity. So if you give me two continuous functions, you add them together, the function is still the sum is continuous. Subtract continuous functions, still continuous. Multiply by a constant, still continuous. Um, Multiply two continuous functions together, you still assign continuous. Divide a continuous function into another one. So long as your denominator is not 0, it's continuous. Um, Raise any continuous function to an integer power, still have continuity. Um, and yeah, and then whenever you have a polynomial, your polynomial is always continuous, and the same is true for rational functions, provided the denominator one is not 0. So your rational function is continuous everywhere where the denominator polynomial is not 0. Okay, and then there's function compositions, which was something that we mentioned back on Monday. So we'd said that if we had the function f of x was x squared plus 1, all raised to the 2/3 power, we could rewrite f of x as g of h of x, where g is x to the 2/3 and h is x squared plus 1. So again, remember the idea of g of h of x is everywhere in g where you see an x, just replace that by h of x. Now, there's this really nice result for dealing with function compositions, and it says that if g is continuous at a and f is continuous at g of a, then the limit as x goes to a of f of g of x is f evaluated at the limit of g as x goes to a. In other words, what this is saying is that we're switching the order of evaluating the function f with taking a limit, or we're pulling the limit inside the f part. And then if it turns out that in maybe a more general case, you have that the limit as x goes to a of g is some number L, and f is continuous at L, then you can do the same thing. Okay, so let's take an example here. So we'll take the limit as x goes to 0 of x to the 4 minus 2x plus 2, all divided by x to the 6 plus 2x to the 4 plus 1, and then we're going to raise that entire rational function to the 10th power. Okay, so we just said that whenever you have a rational function, it is continuous so long as the denominator is non-zero. And what we can see pretty simply is that at x equals 0, that polynomial is going to be 1. So it's going to tell us that our rational function is going to be continuous at x equals 0. And then from this theorem that we just had, we're going to be able to switch the order of taking the limit with raising this rational function to the 10th power. So in other words, we can take the the limit of our rational function as x goes to 0 and then raise that limit to the 10th power. Because rational functions are continuous everywhere where the denominator is non-zero, we can just plug in x equals 0 and get the limit for the rational function is 2, and then we're going to raise that to the 10th power. So this entire limit is found to be pretty simply 1024. Now, if we didn't have this result about being able to switch the order of taking a limit with evaluating a function, we'd have to do more work effectively. So what this is doing is it's saving us a lot of work. Okay, so we've said what happens when we take a continuous function and raise it to an integer power, and now we might ask what happens when we raise a continuous function to a rational power. So if you give me f of x raised to the m divided by n, that function is going to be continuous everywhere where f is continuous in the event that n is odd, and if n is even, then f raised to the m divided by n power is continuous at all the places where f's continuous and also positive. But we should point out this doesn't say anything about what happens if f is 0 or negative. So we do need to investigate those on their own. So let's go and look at where the square root of 9 minus x squared is continuous. Okay, so the first thing that we can say with this is we are raising 9 minus x squared to the 1/2 power. Well, 9 minus x squared is a polynomial, so it's continuous everywhere. So from this theorem, we just need to look at all of the places where 9 minus x squared is positive. Right, so the first thing that we can say is that our function is going to be not defined for any x value that is less than minus 3 or bigger than 3. And the reason for that is that if x is less than minus 3 or bigger than 3, x squared is going to be bigger than 9. So then 9 minus x squared will be negative. We'll have the square root of a negative number, which will be imaginary. So f of x will not be defined for x values to the left of minus 3 or to the right of 3, and clearly f will be discontinuous at those points. For any x value in between minus 3 and 3, 9 minus x squared is positive, So our theorem tells us that f will be continuous at all of those points, so we just need to ask about what happens at x equals 3 and x equals minus 3. Well, at those points, f is going to be 0, so the function is defined, and then we need to see, does the limit exist at either of those 2 points? Well, if we look at the limit for f of x as x goes to 3, we'd run into the same problem about the right side limit not existing. Because the right side, when you take the right side limit, you're going to be looking at x values where x squared is bigger than 9, so f is not going to be defined at any of those values. That will tell us that the right side limit does not exist at x equals 3, and similarly the left side limit at minus 3 doesn't exist, so the limit of f of x as x goes to 3 and also minus 3 will not exist, which tells us that f is discontinuous at those 2 points as well. So the only places where f is going to be continuous are in between minus 3 and 3. Okay, so there's also a slightly modified definition of continuity to look at left and right continuity. So the definition is basically the same as what we had for left and right limits. You have the exact same checklist as we had earlier. You just replace the limit by either the left limit or the right limit as appropriate. And then we could ask about continuity over an interval. So a function is said to be continuous on some interval I if it's continuous at every point in I. And if you're looking at a at a closed interval, all you need to have is right continuity at A and left continuity at B, because you're only concerned about what's happening on the inside of that interval. You're not concerned about what happens outside of it. Okay, so then we have some special functions. So we have trig functions, we have inverse trig functions, we have exponentials and logarithms. And we're just going to take it as given that all of these functions are continuous everywhere where they're defined. Okay, so some examples of those. So let's go and look at the limit as x goes to 0 of cosine squared minus 1, all divided by cosine of x minus 1. And then we'll look at a second example after that. Okay, so the first thing that we could do is we can notice that our numerator is a difference of squares. We have cosine squared minus 1 squared. So we can break the numerator up into a sum and a difference, and then we can cancel away the cosine of x minus 1 factors in the numerator and denominator. And when we do that, we get left with a limit as x goes to 0 of cosine of x plus 1. And because we've said cosine is continuous everywhere where it's defined, we get to just plug in x equals 0, so we get cosine of 0 plus 1, which is nicely 2. Okay, well then how about the limit as x goes to 1 of the fourth root of natural logarithm of x plus the arctan of x? Well, here, the arctangent part we just said is defined everywhere, or it's continuous everywhere where it's defined, and arctangent is defined at 1. So that part won't be a problem. So what we need to ask is, what about the fourth root of natural logarithm? Well, the natural logarithm is defined at x equals 1, and it's 0, which should set off red flags immediately. Because we're looking at the fourth root of a function that's evaluating to 0. And as it turns out, when you take x values that are to the left of 1, the natural logarithm will be negative. So what we'll be looking at is fourth roots of negative numbers, and those are also imaginary. So it tells us that the left limit at x equals 1 won't exist, so the two-sided limit won't exist. So we'll say that this limit does not exist. Okay, so the last thing that we want to do is we want to look at one place where we can use continuity, and that is in what's called root finding. So there's this very nice theorem that takes advantage of continuity. It says if you're given a continuous function over some interval a to b, and you're told that there's some number L in between the endpoints f of a and f of b, So maybe f of a is bigger than f of b, or f of b is bigger than f of a, doesn't matter. You get some number L that's in between them. Then there's going to be some number c in between a and b, so that f of c is L. So kind of one way that we could kind of think about continuity simplistically is that whenever you have to draw your function, you have to draw it without lifting your pencil, right? And we'll see how that's kind of useful in these examples. So what we're going to do is we're first going to show that f of x equals x cubed minus x minus 1 has a root in between 1 and 2. So remember, a root means any place where the function evaluates to 0. And then we're going to show that some other function has 3 roots in the interval minus 4 to 4. Right, so using the intermediate value theorem, the first thing that we probably want to do is just go and look at what the two endpoints evaluate to. And in this case, f of 2 is 5, and f of 1 is minus 1. And what we've said is, if you have to go from this dot down here to this dot up here without lifting your pencil at any point, you have to pass through the x-axis at some point. And because you have to pass through the x-axis at some point, that will tell us that that there's going to be some c value in between 1 and 2, so that f of c is 0. And that's really all we need to conclude. So in general, for an intermediate value theorem, all you want to do is just say, you want to establish that your function is continuous, and then go and say, well, my, say, right endpoint is bigger than 0, my left endpoint is less than 0, so by continuity, my function has to have some point in between my left and right endpoints where the function evaluates to 0. Right, so pictorially, if I just drew, say, a dashed line between them, we can see that our function is passing through the x-axis here. So pictorially, that would also tell us, hey, we have a continuous function here, and we have to pass through the x-axis at some point to get from minus 1 to 5. Right, and if we actually plotted the function, what we would get is this. So it would tell us that the actual place where f is evaluating to 0 looks like it's about 1.33, give or take. Okay, so then we have our second example. So what we want to do here is we want to show that x cubed minus 15x plus 1 has 3 roots in between minus 4 and 4. So what we can do is we can start by doing the same thing. So we'll look at the left endpoint and the right endpoint. Our left endpoint here is conveniently minus 3, and our right one is 5. So that tells us we have to cross over the x-axis once. But so far that's all. And what we need to do is show that we're actually going to pass over the x-axis 3 times. So one thing that we could do is say, well, all we're doing really is we're picking up that we start below the x-axis, we finish above the x-axis as we move from minus 4 to 4. But we could hit the x-axis 3 times in between minus 4 and 4, and what we'll do is we'll go and split up our interval. Right, so what we could do is we could say, well, let's also just split this up as an interval going from minus 4 to 0, and then another interval going from 0 to 4. And what we see here is that in between 0 and 4, we have that f of minus 4 is negative, f of 0 is positive. So in between minus 4 and 0, there is also at least one root, so one place where we're going to hit the x-axis. But then between 0 and 4, they're on the same side of the x-axis. So it would be really, really nice if between 0 and 4, we went under the x-axis and then we came back. So what we'll do is we'll split up the interval between 0 and 4. So what I'll do is I'll then go and split up our interval and look between 0 and 1, and then also 1 and 4. And what we see is that f of 1 is negative. So because f of 1 is negative, our function has to hit the x-axis between 0 and 1, and then because f of 1 is negative and f of 4 is positive, we have to hit the x-axis again going from 1 to 4, and that's going to give us the 3 roots we desire. So we're going to have 1 in between minus 4 and 0 because f of minus 4 is negative, f of 0 is positive. Then we're going to have another root in between 0 and 1 because f of 0 is positive, f of 1 is negative. And then we get our third root in between 1 and 4 because f of 1 is negative, f of 4 is positive. And this is the main idea of using an intermediate value theorem argument to show that you have a root in an interval. Right? If we wanted, we could go and plot the function, and what we'd see is the first root's showing up pretty close to minus 4, the next one shows up pretty close to 0, and the next one shows up at about 3.8 or so. Okay, so I think that's everything that we need to talk about for continuity. There'll be a worksheet over continuity sitting in the WILE courses. Please fill that out and turn it in by Monday, and also turn in your homework by Monday. All right, and I shall see you all in the next video.